In this lecture, we start looking at principal component analysis, or PCA. Now let me start off by giving an overview of PCA. The purpose of principal component analysis is to investigate the extent and the nature of the variability in a multivariate dataset. Principal component analysis can be used to discover the true dimensionality of a multivariate dataset. Now, what do I mean by that? Well, a dataset consisting of p response variables has p dimensions throughout which it can vary. A particular p-variate dataset may not vary throughout all p dimensions available to it, however. In fact, a dataset may exhibit significant variability in only a few dimensions. This can occur, for example, when the variables are highly correlated. In a dataset with p variables, p new variables, called principal components, are created using all p of the original variables. The principal components are useful in determining the number of dimensions in which the dataset exhibits significant variation. Attention can be restricted to those dimensions within which a dataset exhibits significant variability through the use of the appropriately selected principal components. So statistics can be thought of as a study of variation and analyzing variability of multiple variables and looking at the relationships in terms of the variability between those variables. So in order to be useful, a dimension has to have significant variation within that dimension in order to provide information. If a response variable, for example, has no variability, if all the values are constant, then it can add nothing to the analysis. It provides no information about the experimental units under consideration. So there has to be some variation in the responses and in the dimensions within which those responses vary. And so the idea behind PCA is to identify those directions in which there is significant variation and to restrict attention to those directions. Now, principal component analysis can be used to check for outliers by using the principal components themselves via plots and other kinds of quantitative techniques, for example. Principal components can be used to check for groups or clusters of observations. Principal components can be used to check for violations of distributional assumptions, such as violations of the multivariate normality assumption. Principal components can be used in regression analysis to reduce the number of explanatory variables and to eliminate multicollinearity in the explanatory variables. So this is done by using the principal components as input variables to the regression models. By construction, and we'll talk about this later, but by construction the principal components are themselves uncorrelated. And so that completely obviates the problem of multicollinearity when used as input variables to a regression analysis. Now let's talk about the distributional framework and get some notation set up so that we can talk about principal components. So we're going to let bold X be a p by 1 random vector that has, ultimately we're going to assume that these vectors have a multivariate normal distribution with mean vector mu sub x and covariance matrix cap sig sub x. And this is a p-dimensional multivariate normal distribution with rank p. And so here we have, I'm showing the notation with these, with the mean vector and the covariance matrix expanded out, so you can see the entries in the mean vector. Mu1 is the mean for variable x1. Mu2 would be the mean for the variable x2, and so forth down to mu sub p, which represents the mean of the variable response variable xp. Then we have the covariance matrix. It's a p by p. And in this case, it's going to be a positive definite covariance matrix. When we say that the normal distribution has rank p, the implication of that is that the covariance matrix is positive definite. Not only is it non-negative, but it's positive definite. All right, and so in this covariance matrix, we recall that we have the variances down the diagonal, and then on the off diagonal, we have the covariances. So sigma 1, 1 is the variance of x1, sigma 2, 2 is the variance of x2, and so forth down to sigma sub pp, which is the variance of x sub p. In addition, sigma sub 1, 2 is the covariance of x1 and x2. Sigma 1p, for instance, is the covariance between x1 and xp. And remember that this is a symmetric matrix. So sigma 1, 2 numerically is the same as sigma 2, 1 because sigma 2, 1 is also the covariance of x1 and x2. Now, there are p response variables comprising the response vector, and so there are p principal components available to us. So when we have p response variables, then there are p principal components available to us that we can construct and use. And I would also just reiterate what we said a second ago, that the calculation for each of the p principal components, each principal component is calculated using all p of the original variables. Now let's look and see how we derive them. So some definitions. The first principal component of the distribution of x is the random variable, which I'll denote by y1, defined to be a linear combination of the x response variables, the p response variables contained in the x vector, let's put it that way. And that linear combination is represented in vector format this way. So this would be the vector a1 prime times the x vector. So again, this is a linear combination of the original x variables. So it's a linear combination of these variables here. And we're denoting that linear combination by y1. So the first principal component is the random variable y1, which is a linear combination of the original x variables that has maximum variance. That has maximum variance subject to the constraint that the coefficient vector a1 has squared length 1. All right, and the reason that we have that constraint is that we could increase the variance without bound by making the vector a1, the coefficient vector, longer and longer and longer and longer. So to get rid of that problem, we set the constraint that the coefficient vector has to have squared length 1, and then we look for such a vector a1 for which the variance of the resulting random variable y1 has maximum variance. So what we're doing here, so that's the mathematical problem, or the statement that we're trying to solve. It's a mathematical statement, and we're trying to find the linear combination of the original response variables that has maximum variance. And the resulting random variable is called the first principal component. Now for subsequent principal components, we do something similar. So for j going from 2 up to p, the jth principal component of the distribution of x is the linear combination a sub j prime times x, which I'll denote the resulting linear combination by y sub j. So the jth principal component is the linear combination of the original variables that has maximum variance subject to the following constraints. Again, the coefficient vector has to have square length 1. And in addition, the jth principal component is uncorrelated. It's got 0 covariance with all of the previously obtained principal components. So for example, when we find, once we've found the first principal component, when we go to find the second principal component, we find the linear combination of the original x variables that has maximum variance subject to the constraint that the resulting random variable y2 is uncorrelated with the first principal component. Likewise, when we go to find the third principal component, we're looking for that linear combination of the original variables that has maximum variance subject to the constraint that the resulting random variable, y3, is uncorrelated with both y1 and y2, and on and on and on. So when we get down to finding the pth principal component, we're looking for the linear combination of the original variables that has maximum variability subject to the constraint that the resulting random variable is uncorrelated with all of the other p minus 1 principal components. Now, how do we find the first principal component? Well, let me just point out first that you probably noticed that the slide number went from 7 up to 16. So there's a lot of work in going from the specification of what the principal components represent and the mathematical problem to be solved, and the method by which we find the principal components. So let me find the slide there again. Okay, so we're back here on slides 5, 6, and 7. We're specifying what the properties that the principal components must satisfy, and starting in 16, I'm giving the results of a summary of how we actually find the principal components. So in the intervening slides, I'm going through some mathematics on how these are derived, and that's really not important for us to dwell on in this class. This is an applied class, and so we're not going to focus on the derivation. We're going to focus on the result, and then we'll go from there. So the first principal component is given by this linear combination of the original x variables, a linear combination provided by the coefficients in this vector that I'm denoting by C1 as opposed to A1. Okay, and I'll explain that in just a second. But the first principal component is given by this linear combination of the x variables. Okay, we can represent that using vector notation this way, or we can represent it as using summation notation as we've done here. Now, where do we get this vector of coefficients C1? Well, C1 is the length 1 characteristic vector of the covariance matrix corresponding to its largest characteristic root, lambda 1. Okay, now in the previous lecture, we looked at characteristic roots and characteristic vectors. And in that lecture, we explained why we were looking at these things, because many of the procedures that we use in multivariate analysis have their solution in characteristic roots and characteristic vectors. And so this very first application or methodology in multivariate statistics that we're looking at has as its solution the idea of characteristic roots and characteristic vectors. So again, to find the first principal component for this distribution, we look to the covariance matrix. We find the largest characteristic root of that covariance matrix, cap sig. That largest characteristic root is denoted lambda 1. Corresponding to lambda 1, there is a length 1 characteristic vector, C1, of cap sig. And it is that coefficient vector, C1, that characteristic vector, from which we get these coefficients that we use to construct the linear combination of the original variables. So that is how we obtain the first principal component. Now, I would point out that if the original response vector, x, is multivariate normal, p-dimensional multivariate normal, then this first principal component, y1, which is a univariate random variable, has a univariate normal distribution with mean mu sub y1 and variance sigma squared sub y1, where the mean of y1 is given by this same linear combination, not of the x vector, but of the mean vector. So to find the mean of y1, the first principal component, we just take the same linear combination. We use these same c values and apply them to the, let me find it here, to the mean vector. And then the variance of y1 is very easily found, and it is equal to lambda 1, which is the largest characteristic root of cap sig. So we're not going to have to do any calculation to find the variance of y1. That mathematics has already been done, and I'm just giving you this very nice and handy result that the variance of the first principal component is the largest characteristic root of the covariance matrix of the original variables. And so remember, the goal, the stated problem to be solved in principal component analysis was, at least in terms of finding the first principal component, find the variable, find the linear combination of the original random variables that has maximum possible variance. And what this is telling us is that maximum possible variance is equal to the largest characteristic root of the covariance matrix. So when we construct the first principal component in this way, then it has a variance equal to lambda 1. It is normally distributed as long as the underlying random vector is multivariate normal, and the mean of that random variable y1, the mean of the principal component y1, is given by the same linear combination of the mean vector. Now, to find the second principal component, we need to find the vector a2 such that the variance of y2 is as large as possible, subject to the following two constraints. Again, the vector a2 is of squared length 1, and y2, the resulting random variable, has zero covariance with y1. It's uncorrelated with y1. Now, how do we get that? Well, the second principal component is given by this linear combination of the x vector. You see here we've got different constants, c12 times x1 plus c22 times x2 and so forth out to cp2 times xp. Now, where do we get these coefficients? Well, the coefficient vector c2, again, is a characteristic vector of cap sig. It's the length 1 characteristic vector of cap sig corresponding to its second largest characteristic root, lambda 2. And so again, the new variable, the new index, the second principal component y2, as long as the underlying x vector is multivariate normal, y2 will be univariate normal. The mean of y2 will again be equal to this linear combination of the mean vector, and the variance of y2 will be lambda 2, which was the second largest characteristic root of cap sig. And then finally, the covariance of y2 and y1 will be 0. By construction, the principal components are uncorrelated. Now, in general, it can be shown that for each k going from 1 to p, the kth principal component of x is given by this linear combination of the x's, c sub k prime times x, where c sub k is the length 1 characteristic vector of the covariance matrix of the x vector, corresponding to the kth largest characteristic root of cap sig. Now, so the problem of finding the principal components of the multivariate normal distribution with mean mu sub x and covariance matrix sigma sub x therefore boils down to finding the characteristic roots and the characteristic vectors of the covariance matrix cap sig. So this is a great example of why we looked at characteristic roots and characteristic vectors in the first place. All right, because the solution to this problem and the statement of the problem, the mathematical statement of the problem, was find these indices for which this uncorrelated set of indices, this uncorrelated set of new variables, linear combinations of the original variables, which exhibit maximum variability in p dimensions. Now let's put the p principal components together into a p by 1 vector. All right, so we'll denote that vector by bold y. So the original response variables were x's, right? And we denoted the vector of original response variables by bold x. y1 through yp are the principal components, and we're going to denote the vector of principal components by bold y. Now, if the original x vector is multivariate normal, in fact p-dimensional multivariate normal, then it can be shown that the principal components have a multivariate normal distribution as well. In particular, the vector of principal components is again p-dimensional multivariate normal with mean vector given by this vector here, and this just takes the information that we stated before and puts these individual means of the y's into a p by 1 vector. And then the covariance matrix of the vector of principal components is this p by p diagonal matrix. Notice that all of the off-diagonal elements are zeros. Again, that's because the principal components by construction are uncorrelated. They have covariance 0. Down the diagonal, we have the variances of the principal components. So the variance of y1, again, is lambda 1, the largest characteristic root of the covariance matrix of the original response vector. Lambda 2 is the variance of y2, and so forth down to lambda sub p. Now, one of the purposes of principal components is for the purpose of dimension reduction. So we measure p response variables, but in many cases we want to reduce the dimensionality from p down to something that's more manageable. For example, something that's more manageable for the purpose of for plotting, printing out graphs, and things like that. And so, as stated previously, as we've said, we want to identify the true dimensionality of the data set. We don't want to artificially reduce the dimensionality. We want to identify the true dimensionality and then reduce the dimensions to that true dimensionality if possible. So with this in mind, how many principal components should we use? Well, let's go back to the original covariance matrix, or the covariance matrix for the original response vector, cap sig. And so here we have the elements within that p by p covariance matrix. Now, we can define what we might call the total variability associated with the distribution to be the sum of the variances. So the sum of the diagonal entries in this covariance matrix. So the variance of x1 plus the variance of x2 and so forth down to the variance of xp. Now recall that the trace of a square matrix is the sum of the diagonal entries in that matrix. And so the total variability associated with the distribution is equal to the trace of the covariance matrix, which I've denoted here. Now recall from our discussion of characteristic roots that the sum of the characteristic roots of a matrix is equal to the trace of the matrix. All right? So the sum of the characteristic roots of a matrix is equal to the total variability associated with the original response vector. So as we've shown, the characteristic roots of the covariance matrix are the variances of the principal components. The implication of this is that the sum of the principal component variances is equal to the total variability associated with the original covariance matrix. In other words, the trace of the principal component covariance matrix is equal to the trace of the original response, the trace of the covariance matrix of the original response vector. Okay, so the sum of the lambdas is equal to the sum of these sigmas, which are the variances of the original variables. So here we have the sum of the principal components. Here we have the sum of the original variables, and those two sums are equal. By using the principal components instead of the original variables, we therefore don't lose any of the variability existing in the original variables, as long as we use all p principal components. Now, the thing is that some of those principal components may not have very much variability, and so we may choose to exclude principal components which do not exhibit much variability. So the proportion of the total variability accounted for by the first k principal components is given by this ratio. The sum of the first k lambdas, the characteristic roots, divided by the sum of all of the characteristic roots, which again is the total variability associated with the original response variables. And so with this in mind, one approach to choosing the number of principal components is to choose k so that a certain proportion of the total variability is accounted for. So it's common, one common rule of thumb is to choose k so that that at least 80% of the total variability is accounted for by the principal components that are being used. Now, you may choose to use a different percentage, that's fine, but that's one common convention. Another method of choosing the number of principal components is it involves inspection of what's called a scree plot. Now, a scree plot is it's a graphical method. It's a scatter plot of the characteristic roots versus their index number. So in other words, it's a scatter plot of y1 versus on the vertical axis and 1 on the horizontal axis. And then we would plot lambda 2 versus on the vertical axis at 2 on the horizontal axis and so forth. So we're plotting the values of the lambdas against the values of their subscript, basically. And so by identifying where the scree plot starts to level off, one can make a determination as to how many principal components to use. So the scree plot, if you think about it, visualize it in your mind, it's going to be, as you go to the right, it's going to be a decreasing function. And in many cases, you're going to have a very steep decline at first, and then it's going to level off. And so what we're looking for is the point at which it starts to level off. And we call that point the elbow. All right, so you're looking for the elbow in the scree plot. And typically what you would do is find the elbow and then back up one principal component. So for example, if you've got, if p is equal to 10, so you've got p principal components, you would, the scatter plot would have p points on it. The points would be connected by straight lines. Let's say that the elbow occurs at the third principal component, or the third lambda. So there's a decrease from going from 1 to 2, and then from 2 to 3. But from 3 to 4 and so on, maybe it's fairly level, or the rate of decrease is much less than it was in the first two lambdas. And so what you would do then, you would have the elbow at the third characteristic root, and so you would back up one, and you can use that criterion to use the first two principal components. Now, we're going to be looking at some examples of principal components. I think that this is probably a good place to stop this video. We'll pick up the examples in the next lecture video.